We are trying IGCSE Physics worksheet on waves, question number 20 from 0625 paper 22, March 2021. What is the approximate wavelength in air of highest frequency sound that can be heard by a normal healthy person? So what I know is frequency times wavelength. Okay, let's try. Speed equals frequency times wavelength, right? So it's V equals F lambda. V equals 330 meters per second. Frequency is 20,000 hertz, because we know the normal hearing is 20 to 20,000 hertz. It times lambda, sending 20,000 to the other side, 330 divided by 20,000. Use calculator, you get 0.0165. Now, which is closer to 0.0165? That's because if you round it up to two decimal places, it becomes 0.02. So the answer is A. Let's try the next one. What causes the change in direction when the light travels from air into glass? When the light travels from air into glass, the ray gets slower. The speed becomes slower, right? Because glass is a bit more denser than compared to the air. So whenever from lighter medium to denser medium, the speed will decrease. So what changes is the speed, because A is the amplitude of the light changes, the color of the light changes, the frequency of the light changes, the speed of the light changes. Here, for multiple choice questions, you have to cross out the wrong ones. The amplitude of the light changes. No, it doesn't change. Amplitude will, okay, sound create, if it is for sound, loudness. So for light, it will be the brightness. The color doesn't change. It's monochromatic light. If it is one monochromatic light, then it doesn't change. Okay, what about next one? The frequency of the light changes. It doesn't change. Frequency of the light is same, and the speed changes. Light from two rays with an angle of incidence 60 degrees pass into dilute solution and concentrated sugar water solutions. The refractions are shown. Okay, for dilute solution, the angle of incidence is 60 and angle of refraction is 40. For concentrated sugar solution, angle of incidence 60 and R angle of refraction is 35. Right? Which row is correct? The refractive index as concentration increases and speed through the solution as concentration increase. Right? So we have to think about refractive index as the concentration increase from this solution to that solution, whether it is increasing or decreasing, and the speed we have to think about whether the speed as we go from this to that, whether the speed also increase. All right, let's try. Now this is less concentrated solution, and this is higher concentrated solution. Now higher concentrated solution has more density. So when any ray passes from less density to higher density, definitely the speed decreases. So I'm done with speed, right? Here it says speed decreases, fine. Increases, wrong. Decreases, yes, wrong, right? Now let's try about refractive index. Now refractive index of water. What is refractive index of water? It's 1.33. Speed of refractive index is speed of light in air or vacuum rather. So 330 meters per second. And then in the water, the speed whatever it is. So we have to think what is the refractive index. It is, we know eta is 1.33. All right. So no need to remember, I'm just telling you. What is refractive index? It is speed of light in vacuum divided by speed of light in medium, which is water here. But we don't need it here. I'm just refreshing your knowledge. All right. So here, eta equals sine I over sine r. There is another equation. We have two equations, number 1 and number 2. Now eta is, for this first one, eta is sine 60. I is 60 for the first one, divided by sine 40. So sine 60 divided by sine 40, and the answer is 1.347 something. All right, for number 2, the second solution, eta is sine 60 divided by sine 35. Sine 60 divided by sine 35, and the answer is 1.5098 dash dash dash. So if you notice, this was 1.347, this is 1.509 something something. So this also increases. So decreases wrong, increase, increase. Now where both are correct, that's option C. That's how I work out. Let's try number 24. Now 24 says, a thin converging lens is used to produce a sharp image of a candle, right? The various sharp images are produced on the screen by moving the lens and screen backwards and forwards. Which statement is always correct? Now think about this. This is lens, and which lens is it? Does it say converging lens? Converging lens is the convex lens. In convex lens, what kind of image do we get unless it is between principal focus and centroid? It is inverted, right? It is inverted, and it is larger, small, same size. They haven't said anything, but here do you see that they have shown you that the image is here upside down. Upside down means inverted. Let's see. Various sharp images are produced on the screen by moving the lens and screen backwards and forwards. Which statement is always correct? The image is at principal focus of the lens. Does it show? It hasn't shown. They didn't even show where is the principal focus, so don't bother about that. The image is bigger than the object. You can check with the ruler. It looks the same size. The image is closer to the lens than the object. We can't tell because it doesn't show the scale here. If they have shown scale, the distance, we could say whether it is true or false. So I can't say this, I can't say this, I can't say that. Let's try the last one. The image is inverted. It is inverted, upside down, right? Let's try the next one. Next one says, which row gives the approximate speed at which the ultraviolet rays travel in air and in a vacuum? All right. So now it is, I know the speed of light, which is same as ultraviolet waves, right? Ultraviolet rays. It is same as speed of light, 300,000 kilometers per second. But here it is in meters per second. So 300 kilometers times 1000. So it's 300 million, right? Meters per second, which is same as 3 times 10 to the power 2, 6 and 8, right? Meters per second. All right. Speed in air, I know, 3 times 10 to the power 8, fine. Okay, speed in vacuum is just little bit different, but more or less the same in vacuum and air. So it's this, not this, not this. Yes, not that, not that. Which row? Everything is right. That one. So option D is correct. Let's try that one. The diagram represents the sound wave. Okay, these X are, we can tell, compressions and Y are rarefactions. What are the names of parts of the sound wave labeled X and Y? X are rare compression, not amplitude, not rarefaction, not wavelength. Y is not wavelength, a rarefaction, yes, not amplitude, not compression. So it's B. 27. The speed of sound is different in different states of matter. The speed of sound in liquid water is 1500 meters per second, which row correctly compares the speed of sound in ice and the speed of sound in water vapor with the speed of sound in water. All right, let's try. We know three different states of matter: solid, liquid, gas. The light travels or sound travels slowest in gas because the particles are further away from each other. Then liquid because particles are a bit closer to each other, and solid because they are very tightly packed, so they can pass the compressions and rarefactions, which is vibrations, very easily. All right. Now, which row correctly compares the speed of sound in ice? Okay, ice, which is solid, and steam, which is gas. It says in water it is 1500. So solid will be more and gas will be less. More than 1500, more than 1500. Not this, not that. Less than 1500, less than 1500, not more than. Which row is correct for both? It's C. So the answer. Question 6a. Figure 6.1 is full scale diagram showing a converging lens. Converging means the rays meet at a point on the other side of the lens. All right. The two principal focuses f1 and f2. Where the points meet, that's the principal focus. So rays can come from any side. So if they are coming from this side, this principal focus. If they are coming from that side, then this is the principal focus. And the object PO, that's the object. On the figure 6.1, draw two rays from object O of the object to determine the position of the image. Label the image IJ. Measure the length of the image. Alright. One ray should go there, straight parallel to principal axis. This is principal axis. Then from there it passes through the principal focus. That's one ray. The second ray passes through the centroid. This is centroid. Centroid. So one ray passes through the centroid. Right? Okay. Now they are not converging. When they don't converge, what do? We extend the line to the other side. Right? So wherever they meet, that's my answer. That's where the object is. I haven't used ruler, so you might be getting the image bit closer than where I am getting. So not necessarily your answer is wrong, but the problem is I'm not using ruler, so I'm drawing without ruler. So my answer, my image might be, that's what I'm thinking, might be bit further than the object. So you might get image there if you use ruler. Please check. The image length, you have to use ruler. According to mark scheme, it is 2.7 centimeters. You check this, right? All right, let's try next one. It says now next one. All right. Reading the description of the image: diminished, magnified, real. Is it real? No. Can you take it? Can you focus it on the image on the screen? If it was that side, then I would have managed to focus it on the screen. But this is not real image. It's magnified, right? Sorry. Magnified means it's bigger than the object. Then say diminished, magnified, real, not real, so it's virtual. Same way up as object. Yes, it's the same, check. And not upside down compared to the object. State the name of the reflection of a sound wave of ultrasound wave. Echo. Reflection of sound is called echo. 5.1 shows an ultrasound wave being used to scan an internal organ of human body. It's ultrasound transmitter and receiver, internal organ, ultrasound wave. The ultrasound wave has a frequency of 2 megahertz and passes through human source of a sound of a speed of 1500 meters per second. Calculate the wavelength of the ultrasound wave in human tissue. Okay, we need to calculate the wavelength. So what we need, we are given frequency, we are given speed. So it is speed v equals frequency f times wavelength lambda. So 1500 equals frequency 2 times lambda. Lambda is 1500 divided by 2. Lambda is 750. Right? Sorry, it's megahertz. So when it is megahertz, I have to try. V is 1500 megahertz. I'm sorry, I thought it was hertz. So 2 times. Okay, it's kilo, mega, giga, tera, peta. Kilo means 1000 times. Mega is million times. Giga is billion times. 10 to the power 9. So tera is trillion times, 10 to the power 12. Similarly, peta will be 10 to the power 15. So I have mega. Mega means 10 to the power 6. So 2 times 10 to the power 6 times lambda. So lambda is 1500 divided by 2 times 10 to the power 6, which is 7.5 times 10 to the power negative 4. Let's try the next. Figure shows crest of wave from a point source S approaching a straight barrier. Alright. On figure 5.2, indicate and label one wavelength. Right? So this is from crest to crest. It is wavelength, one wave to another wave. That's the wavelength. Alright. Next, B. Number 2. On figure 5.2, draw 3 crests of wave reflected from the barrier. So when these are reflected by the barrier, by this barrier to these waves, right? So what happens are they are split. One here, same, 3. Make sure that this distance is similar, between waves. That's how I should draw. Next, IGCSE Physics 0625, Paper 21, June 2021, Question 21. A water wave passes into region where the wave travels more slowly. As it passes into slow region, what happens to the frequency and what happens to the wavelength of the wave? Okay, so we know the speed equation. Speed equals, okay, we can say speed V equals F, frequency times wavelength lambda. If V increase, since F remains the same, because if F changes, frequency changes, it's no more the same matter, it's a different matter, different wave. So F can't change. So what has to decrease for speed to decrease? Wavelength has to decrease. If speed increases, F remains the same. So to increase change in V, lambda also has to increase. So wavelength has to increase. So here it is decreasing. So frequency remains the same and wavelength decreases. Not this, not decreases, not increases, remains the same. Yes. Remains the same. No. No. Decreases, increasing. No. So this is C. Let's try number 22. Light traveling at a speed of 3.0 times 10 to the power 8 meters per second strikes the surface of glass block and undergoes refraction as it enters the block. So this is speed that is given to me. Speed of light, right? Next one, it says and undergoes refraction as it enters the block. What else is given to me? Okay, what I know is speed of light, or I can say eta, refractive index is speed of light in air or vacuum, I should say, divided by speed of light in medium. So eta is speed of light 3 times 0 times 10 to the power 8 divided by speed of light in medium. So I don't know two things, 1 and 2, that doesn't work. So out of these two I have to find one, either eta, refractive index, or this. So there is another equation. I know eta is sine I over sine R. I is the angle of incidence and R is the angle of refraction. So sine of 55 divided by sine of 33. And the answer is 1.504027. Okay, I can use that. So 1.504027 equals 3.0 times 10 to the power 8 speed of light in medium. So speed equals, I'm sending speed there and this there. 3.0 times 10 to the power 8 divided by 1.5040, right? And the answer is 200 million meters per second, which is 2 times 10 to the power 8 meters per second. Let's try 23. The diagram shows a narrow beam of light incident on a glass air boundary. This is glass air boundary. Some of the light emerges along the surface of the glass and some is reflected back into the glass. Which row is correct? Alright, let's try this. Sorry. Which row is correct? There is example of total internal reflection. If it was total internal reflection, the whole light would have reflected, but here some of light is passing through the parallel to the surface, so it's not total internal reflection. No, it's not. Yes, which means this answer is right. Yes, no. No is yes, yes is no. It's not total internal reflection, right? Next one. Angle theta is the critical angle. Angle theta is critical angle. What happens at critical angle? Critical angle, some of the light passes through the towards parallel to the surface and some may reflect it back. But no light comes out of the surface. So this is example of total internal reflection. Yes, no, no, yes. Which row? Both are correct. Thus A. Let's try next one. Number 24. An object is placed in front of a thin converging lens. The diagram shows the paths of two rays from the top of the object. Converging lens and immerse. What is converging lens? The rays converge, meet at one point. Two beams of light are both the same color of red. One beam is traveling through air, the other one is traveling through water, which means the frequency is same and speed will be different. Each beam has different brightness, amplitude is different. It says both are color red, frequency same. One traveling through air, one traveling through water, speed is different. Each beam has different brightness, amplitude is different. Which quantity is the same for both sets of waves? Amplitude? No. Frequency? Yes. Speed? No. Wavelength? Okay. Forget about that. So it's the frequency. Let's try number 20. The diagram shows wavelength is, okay, that we'll discuss in class. The diagram shows a ray of light in air incident on a glass block. Some of the light, this is angle of incidence, right? Q. Some of the light is reflected, right? Two angles P and Q are marked on the diagram. Which row gives the angle of incidence and state whether the total internal reflection occurs? If it was total internal reflection, then we will not get that ray passing through, because that's the diffracted ray, right? It has, so that's a refracted ray. So this is angle of refraction, this is angle of incidence. We won't get refracted ray. So in total internal reflection, if you get that in angle of incidence and you get the whole ray reflecting back. So that's not the case here. Okay. Which row gives the angle of incidence and state whether the total internal reflection occurs? Angle of incidence is P? No. Q? Yes. Total internal reflection? No. Yes. No. That's wrong. Sorry. I should have returned that. Total internal reflection? No. Correct. That's correct answer. Yes. No. Correct answer? No. So both are correct in C. The diagram shows a ray of light in glass incident on the surface between the glass and air. What happens if the angle of incidence is made larger than the critical angle of the glass? Angle of incidence made larger than the critical angle of the glass. So angle of incidence, if it is larger than the critical angle, there is only reflected ray, not refracted ray, right? So the whole light will come back to the glass like this. All right. What happens if the angle of incidence is made larger than the critical angle? The angle of the reflection becomes equal to 90? No. That is, there is reflected ray, refracted ray, and a reflected ray inside the glass. No, that's for the angle equals critical angle. Critical angle equals the angle of incidence. That's the case where angle of the incidence is critical angle. All right. There is refracted ray only. No. Refracted ray is outside the glass. No. When it is angle of incidence is more than the critical angle, there is only a ray reflected inside the glass. Correct. The sun emits the infrared radiation and light from the sun reaches the earth in 8 minutes. Which row gives correct information about the infrared radiation? Okay, wavelength of infrared radiation, let's discuss that. Is it longer wavelength than light? Yes. Longer wavelength than light? Yes. Shorter than wavelength of light? No. Shorter than wavelength of light? It is longer than wavelength of light. Alright. Time taken for infrared radiation to reach the earth? Same time, because it says 8 minutes light. It's the part of the electromagnetic spectrum, so they all reach the earth the same time. Much less than 8? No. 8 minutes? Yes. More than 8? No. So where is both correct? That's A. Which list shows the regions of the electromagnetic spectrum in order of increasing frequency? So we have written the table, if you notice, in the classwork, right? So it is infrared, increasing frequency. Infrared first, then it's this one, infrared, then visible light, then ultraviolet, and then X-rays. Right? All right. What is ultrasound? You have to learn it, okay, properly. What is ultrasound? A sound wave that are so loud that they damage human hearing? No. We have done, many of us have done ultrasound, right? For different reasons. Maybe not yourself, but your parents. So we haven't lost our human hearing. Sound waves that are too high pitched for humans to hear? Yes. We can't hear them. Sound waves that are too low pitched for humans to hear? No. They are high pitched. Ultra waves are high pitched. Sound waves that are too quiet for humans to hear, that's about amplitude, not about frequency, pitch, high pitch, low pitch, right? Okay. Amplitude, not frequency. Sorry, it's about amplitude, soft sounds. All right. IGCSE Physics 0625, paper 41, November 2021. Explain in terms of behavior of light rays what is meant by principal focus for a thin converging lens. So it is point where parallel rays parallel rays of light meet after passing through lens, or we can say point where parallel rays of light meet or are focused after passing through lens, or point through which rays of light that emerge parallel pass before reaching lens. I think this is better. State what is meant by focal length. It is the distance between the principal focus or we can say principal focus is the focal point also, and optical center of the lens, that, or we can say it is centroid of the right. A lens is used to produce a focused image of an object on a translucent screen. In figure 5.1 shows the object O and its image I. All right. Let me see. I don't have even taken the picture of that page. Just a minute. No. Just let me take the picture first. A lens is used to produce a focused image of an object on a translucent screen. Figure 5.1 shows the object O and its image I. All right, that's image. If you see, that's the image, right? And that's the object. All right. Next one. Consider the straight ray that passes from the tip of O to the tip of I and find the position of the lens. tip of O is this and tip of I is this. So I have to figure out the position, use ruler. It's difficult for me to use ruler. I'm trying my best. I'm trying my best to draw without, ruler. Done. Next one. It says find the position of the lens. So position of the lens, it passes, remember the tip of the object and tip of the image, it passes through the centroid. So this is the line where you can say it's the flow, right? Kind of flow you can call it. So where does it meet the floor? It's this point. So the lens will be here. I can say the lens is, just let me draw a lens like this. It's okay. That's the lens. All right. Find the position of the lens. Mark the position of lens by drawing a vertical line. Okay, I have drawn vertical line. Labeled L. From the top of the grid to the bottom. Done. On figure 5.1, draw a ray that passes through one of the principal focuses and determine the focal length of the lens. So first of all, it should be parallel to the principal axis. Done, right? And then it passes through the, so where does it crosses the flow? I'm calling it flow. Right, so that's the focal length. This is the focal length and that's the focal point of principal focus, F. All right. It says how far is it, right? Determine the focal length of the lens. Okay, so that's 1 centimeter, 2 centimeter and 3 centimeters. 3 centimeters. All right. Object O is a printed document that includes a larger letter R on the side of facing the lens. The top edge of the document corresponds to the tip of O. All right. Object O is printed document that includes a large letter R on the side facing the lens. All right. The top edge of the document corresponds to the tip of O. Figure 5.2 shows the printed document. On figure 5.3, which is this, figure 5.3 is this. Mark a tick in one of the boxes to indicate how the image of the translucent screen appears to someone who is looking at the screen from the point P. Right? Explain. P is, where is P? Explain why image has its appearance. All right, let's see from screen from point P. Okay, printed document, top edge, object O. Okay, R, we don't see where is P. So that means P is anywhere the person is viewing. That's what it means. So it is, which kind of lens is it? Convex lens, right? So convex lens, the image will be reversed, right? And inverted. All right. Reversed and inverted. All right, let's try the next one. The X-rays are electromagnetic waves. Excuse me. Figure 6.1 shows the position of X-rays in electromagnetic spectrum arranged according to the increasing wavelength. All right. So gamma rays, then X-rays, then after gamma rays and I'm so sorry. X-rays are electromagnetic waves. In figure 6.1 shows the position of X-rays in the electromagnetic spectrum arranged according to increasing wavelength. Okay, so these are gamma rays, X-rays. After X-rays, this is the space for ultraviolet rays, then visible light. Okay, then after visible light is infrared. After infrared, it's microwaves, and after microwaves is the radio waves. Okay, you should just do it by heart. These three components of the spectrum are unnamed but labeled J, K, L. State the names of these three components. Okay, J is ultraviolet radiation. Infrared, K is infrared. And L is radio waves. State which of these three components have the lowest frequency. Now it says increasing wavelength. If you notice, increasing wavelength means it is decreasing frequency. Increasing wavelength means decreasing frequency. So which are the least ones? Radio waves. Calculate the frequency of X-rays that have wavelength of 1.2 times 10 to the power -9 meters in a vacuum. So V equals F times lambda. V light 3 times 10 to the power 8 meters per second equals F. Wavelength is given 1.2 times 10 to the power -9. Send it to the other side. 3 times 10 to the power 8 divided by 1.2 times 10 to the power -9. And the answer is, that's F, which is 2.5 times 10 to the power 17 hertz. 2.5 times 10 to the power 17 hertz. Remember to write units, please. Describe one medical use of X-rays. Treating cancer. Okay. All right. And how it is done, because it's 3 marks. So if it was just treating cancer, they wouldn't award 3 marks. So we can write like this: treating cancer, because as X-rays are absorbed by tumor, right, and it is killed. Or X-rays, another, we can write it is, we can use X-rays for shadow photograph. The X-ray that we know, it's called shadow photograph. They are absorbed by bones and we get photograph. All right. Or we can use them in sterilizing medical equipment as they are absorbed by the germs on the equipment and they are killed. Who are killed? Germs are killed. Let me write germs are killed. So you can write one of 3. State one reason why it is necessary to take safety precaution when X-rays are used. They can cause burns. They can mutate cells. So cell mutation. They can do cell damage. Next, they can cause tumors, they can cause cancer, they can damage the DNA of the cell. All right. So you can write one of it because it's just 1 mark. The diagram shows the pattern of water waves as they pass through a narrow gap. Narrow gap. All right. Next one. The diagram shows the pattern of water waves as they pass through narrow gap. Which row names the process shown and describe the effect of using a wider gap? Okay, is it refraction or diffraction? IGCSE Physics 0625 April 22, November 2021. The diagram shows the pattern of water waves as they pass through a narrow gap. All right, that's the gap we are talking about. Which row names the process shown and describe the effect of using a wider gap? Okay, when the water waves passes through a narrow gap, they diffract. So that's diffraction, not refraction, diffraction. If you use wider gap, then the diffraction is less. They spread out less. Not more, less, not more. Which option has both correct? That's C. Number 18. Which row is not correct for a wave on the surface of water? Okay, amplitude, usual meter, correct. Frequency is measured in hertz. Wavelength, the wavelength is measured in meters. Its symbol is lambda, right? And speed is in meters per second. So which is not correct? That's C. The diagram shows how a ray of light refracts when going from air to perspex. Okay, it's going towards the normal because perspex is more denser than the air. This is what is shown in the diagram. The critical angle of perspex is C. Which expression is correct? Okay, so that's sine x over sine z is sine c. All right. Okay, that's, if we remember, in the critical angle is sine c is 1 over eta, and that's on page, let's try that. That's on page, let me tell you page number of the textbook. That was page number 151, and that we got from refractive index, right, which is sine I over sine r is eta, correct? That's where we got it from. So we can say this was eta is 1 over sine c, we can say that. So sine I over sine r. So critical angle is sine c here, right? So sine c from there, I can say, or from there, sine c is 1 over eta, and eta is sine I over sine r. So sine c is 1 over sine I over sine r. So this is denominator and this is denominator's denominator. So denominator's denominator becomes the numerator. So I can say sine c is sine r over sine I. All right, sine r. So that's angle of refraction. This is angle of incidence. So I can say sine c is sine r, which is sine z, over sine of I, which is x. That's the one. Hope you understood. Question 20. It's just simple, pure math, nothing more. It's math, it's not physics, it's math. The diagram shows a ray of light in air incident on a glass block. Some of the light is refracted and some of the light is reflected. So this is refracted and this is reflected. All right. Two angles P and Q are marked on the diagram. So this is angle of incidence. So P is the angle of incidence. All right, let's see which row gives the angle of incidence, P. And the states whether total internal reflection occurs. Total internal reflection occurs only and only if it is the whole of the ray is reflected back. So here some of it is refracted, so it's not total internal reflection. So no is correct and yes is wrong. And P is the angle of incidence, not Q. So both correct, that's A. Next one. The letter F. I'm so sorry. That's angle of incidence says it's Q, not P. I'm sorry, I made a mistake. Because angle of incidence is Q. So that's Q, not P. So that's C, not A. My apologies for that. The letter F is reflected in a mirror. What does the optical image look like? So we know that according to math, the mirror image is like that. So which one is that? B. We have learnt in reflections, right? In maths, that's what it is. Number 22. The sun emits infrared radiation and light. Light from the sun reaches the earth in 8 minutes. Which row gives correct information about the infrared radiation? Now the wavelength of infrared radiation and time taken. So time taken, the speed of the whole electromagnetic spectrum is the same, and wavelength of infrared is longer. So longer than the wavelength of light, yes. Sorry, let's try this. Longer of wavelength of light, longer, yes. No, no. 8 minutes because it's the same time, speed is same. So both correct in A. Let's try the next one. Which statement about electromagnetic waves is not correct? They travel at 3 times 10 to the power 8 meters per second in vacuum. True, because it's the same as the whole electromagnetic spectrum travel at a same speed. They transfer energy. It says not correct. True, they transfer energy. All which waves? Transverse waves travel using transferring energy. They travel at 340 meters per second. No, that's not the true. They travel at 3 times 10 to the power 8 meters per second. Just bit or less same as the speed in vacuum. They are transverse waves. They are transverse waves, which is not true. C. What is ultrasound? Sound waves that are so loud that they damage hearing? No. Sound waves that are too high pitched for humans to hear? Yes. Sound waves that are too low pitched for humans to hear? No. Sound waves that are too quiet for humans to hear? No. So that's B. 6.1. IGCSE Physics 0625, paper 42, November 2021. The figure shows particles of material which are in which a sound wave is traveling. So you see the points which are closer together, they are compression. That's compression, and further away from each other, rarefactions. On figure 6.1, mark number 1, the center of compression with C. So center of compression is the C, and that's C. All right, that's C. The center of rarefaction. So rarefaction is that that, right? One wavelength with a double-ended arrow. So rarefaction to rarefaction is one wavelength, you can say. Or you can even say compression to compression is also one wavelength. So either this or that. Circle one value of from the list, which is speed of sound in water. We know that it's 1500 meters per second. The wavelength of sound wave in water is 12 centimeters. Calculate the frequency of this sound wave using your value from B. So speed equals frequency times wavelength. 1500 equals frequency times, okay, wavelength is 12 centimeters, but wavelength should be in meters, so divide by 100. So that's my frequency times wavelength. So that's 1500 times 100 over 12 is frequency, and which is 1250000, hertz, which is same as 13,000 hertz. Two significant figures, because I'm writing two significant figures because they have given answer in two significant figures. But if you write 12,500, okay, you have to see the cover page of the physics book, and what accuracy does it say. You will read, right? And I have sent you papers. I'll send you papers and you see what is the frequency, what is the accuracy, and use that accuracy. State and explain whether the sound in C is ultrasound. No, it's not. It's not ultrasound. Explanation. Ultrasound has frequency more than 20,000 hertz because human hearing hearing is 20 to 20,000 hertz. So it's about 20,000 hertz. Ultrasound has frequency above 20,000 hertz. Figure shows ray of light approaching face AB of glass prism on refractive index 1.5. On figure 7.1, accurately draw the path of ray within which the prism from face AB to face AC. You will need to make measurements from figure 7.1 and carry out calculations. Alright, let's try this. First of all, I need to draw normal ray. So I'm drawing, okay, remember you have to draw again because mine on this won't be perfect. But this question I have done on the paper and I have calculated the answer there. So the angle of incidence, this is angle of incidence, and I have calculated it to be 60 degrees. All right, so now refractive index is eta is sine I over sine R. What am I doing? Because I need to figure out what's this angle. So to calculate that angle, I have to figure out how much is R. So I'm given 1.5, eta is 1.5. Sine I divided by sine R. So sine R, so that's sine R is sine I over 1.5. Send sine to the other side because I need to calculate R, not sine R. So R is sine inverse sine I over 1.5. And the answer is 35.26 approximately 35.3 degrees. So I use protractor again and draw a line of 35.3 degrees to hit AC. On AC again at 90 degree to AB, I draw one normal. So that's normal. Now it says determine the angle of incidence of this ray when it strikes AC. So check how much is this angle, that angle. So use calculator, use protractor and check, that's 10 degrees. Without further measurements or calculations, sketch on figure 7.1 the approximate path of the ray passing through face AC. Now it comes out. When it comes out, it moves away from the normal. So that goes away from the normal. So that's path. That's how I should draw. Alright, the next one now. The next question says, without further measurements or calculation, sketch. Already that's done. Figure 7.2 shows ray of light traveling within an optical fiber. Right? Now, I'm sorry, there is no question there. Just a minute, let me see what was the question there. Question 24. An object is placed in front of thin converging lens. The diagram shows paths of two rays from the top of the object. An image of the object is formed on a screen to the right of the lens. How does the image compare with the object? Alright, so first let's try. One ray should pass parallel to the principal axis. Which is principal axis? This is principal axis. Then it should pass through the focal length on the other side. They haven't mentioned focal length, but that ray passes through this point. That means this is its focal length. Right? So principal focus, the point is called principal focus. It should pass through principal focus, and the length is focal length. All right. Second ray passes through the centroid, the center of the lens. So that's centroid. Extend it. Extend this. Right? On the paper, you can during exam you can draw, and then check where you get object. Then check if the image is larger and or smaller compared to that, because you can use it for magnifying also, magnification ratio. So image is larger, all right, and inverted. It is inverted. It's larger, not same way up. Same way up is that. It's smaller, it's not smaller. And sorry, it's not smaller and not, yes, it is inverted. It is smaller, no, and it is same way up, no. A remote control vehicle is traveling. Even if you found the correct answer, you better cross check each and every option and make sure that the option you have chosen is correct one. A remote control vehicle is traveling on a surface of a planet. The vehicle senses an obstacle ahead. It sounds radio message to the control room from where it is being controlled. The control room is 2.4 times 10 to the power 5 kilometers away from the vehicle. The control room sends message back to the vehicle telling it to stop. What is her minimum time? What is the minimum time that elapses between the vehicle seeing the obstacle and receiving the message back from the control room? All right, let's try this. First of all, speed equation. Speed is distance over time. Speed equals distance over time. So distance is 2.4 times 10 to the power 6, but that's 2, and from going there is 2.4 times 10 to the power 5. Coming back is the same, so I can write 2 times the distance, 2.4 times 10 to the power 6. All right, and that's how much? Kilometers. But let's change it to meters. So meters will be times 1000, so which is times 10 to the power 3 over times. Okay, so let me try again. I can write, where is the space? All right, I can write here. Speed is given, we know 3 times 10 to the power 8. All right, so let's try like this. Time is distance over speed. I can try that. So distance is 2 times 2.4 times 10 to the power 6 kilometers. Let's change into meters times 1000, which is 10 to the power 3 meters, over speed of the light is 300,000 kilometers per second, right? Let's change it into meters. So 3 times 10 to the power 8. 3 times 10 to the power 8 meters per second. All right. Use calculator. You will get 16 seconds. A sound wave is traveling onwards from a loudspeaker into surrounding air. Here are 3 statements. The air pressure is lower at a rarefaction compared with undisturbed air. The density of the air is less at compression compared with undisturbed air. The distance from a compression to rarefaction equals half a wavelength. Alright, the sound from which statement about the sound waves are correct? 1 and 2 only, 1 and 3 only, 2 and 3 only, 1, 2, 3. The air. So let's check the statements again. The air pressure is lower at rarefaction, yes, compared with undisturbed air because the particles move away from each other, perfect. The density of air is less at compression compared with undisturbed air, false, because the density is more. The particles are in the compression, they are closer to each other, so there are more particles, so density will be more. The distance from the compression to rarefaction is equal to half a wavelength, yes, because compression to rarefaction and compression then rarefaction, so that's half a that is wavelength. So it says compression to rarefaction is half a wavelength. This is wavelength, full wavelength. So that is half a wavelength. So that's correct. So 1 and 3 only. So that's B. Not 1 and 2. 2 is wrong. 2 and 3, 2 is wrong. 1, 2 and 3, 2 is wrong. The sound from loudspeaker must pass through 2 materials to reach a microphone. Which combination of the materials give the shortest time for the sound to reach the microphone? All right. There is something missing. The options are missing there. So I'm writing options there. So that's A, B, C, and D. Then I write that. And that's material 1. Or I write material 1. And then it is material 2. Okay, material A, it says material 1 is air and second is hydrogen. Option B says the first one is air and second is water. Third one says it's copper and aluminium. And third one says it's water and oil. Now, I don't know much about loudspeakers, but let's use common sense. Consider you don't know much about, okay, we all don't know much about loudspeakers. So let's use common sense. In the loudspeaker that we use, it's a speaker, right? So in speaker, we don't know, there can be air, right? There can be air, for example, and hydrogen. If it is air and hydrogen, that means there is nothing inside. If there is nothing inside, why do we need? Because there is air all around us, so we don't need it. So that's not true. Second, air and water. For sure, there is no water, right? Because electricity and water don't go together. C, copper and aluminum. Yes, it can be. Why? Because it has to be solid. We have seen it is a solid. And water and oil, no. So it's C. IGCSE Physics 062541 June 2021. On figure 6.1, mark 2 points, each at center of different compressions. Label both of the points C. All right, let's try that. So that's compression is where it's close to each other, and the point is C here, where these two are close. So that's point C, that one, right? All right. B, the speed of sound in air is 330 meters per second. Measure the diagram and determine the frequency of sound. So I know the wave equation. V equals F times lambda. Speed equals frequency times wavelength. Speed is 330. Frequency is F times wavelength is 0.052. So 330 divided by 0.052 is frequency. Use calculator, you get 6346.15 dash 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 dash, approximately 6346 hertz. Let's try the next one. C. The wave reaches a barrier. Figure 6.2 show the wave passing through a gap in the barrier. That gap, right? This is gap. Okay, this is gap. All right. All right, let's try. This is the barrier. The frequency of the wave is increased to value many times greater than the value obtained in B. Okay. So which means the value was 6346 in B. Right? That's the one. Okay. The frequency of wave is increased to the value many times greater than the value obtained in B. Describe and explain two ways in which a diagram representing the wave with greater frequency differs from 6.2. So I can write compressions or rarefactions closer. If you see, right, closer or more compressions or rarefactions in the same distance. Number 2, less diffraction or spreading out. Okay, a few hours later, a student noticed that reading on voltmeter is greater. Explain what can be deduced from this observation. Okay, that's not the part of this. I think that's from electricity. So this is not part of this. I think I have made a mistake somewhere. Okay, IGCSE Physics 0625 paper 22 June 2021. A water wave passes into region where the waves travel more slowly. As it passes into the slow region, what happens to the frequency and what happens to the wavelength of the wave? All right, it passes from, it says, into region where it travels more slowly. So frequency, okay, it's about frequency and wavelength. Frequency decreases, no, it remains the same. Why? Because if frequency changes, the wave changes. So its wave is still the same, right? So it remains the same, fine. It's no more than the same wave. If it is water wave, if the frequency changes, it's not water wave then, right? It's some other wave now. Next one, wavelength remains the same. No, wavelength, then the speed doesn't change. If the wavelength decreases, then only it travels more slowly. The wavelength increases, no, then it will travel faster. All right. Next one. Number 22. Light traveling at a speed of 3 times 10 to the power 8 meters per second strikes the surface of a glass block and undergoes refraction as it enters the block. The diagram shows ray of light before and after it enters the block. What is the speed of light in the glass? Now here we have angle of incidence, which is I, and angle of refraction, which is R. So we know the equation eta equals, which is refractive index, equals speed, okay, sine I over sine R. Why am I using this? Because what I need is refractive index is speed of light in, what is it, air or vacuum divided by speed of light in glass. But for that, what I know is speed of light in air, right? That one I know. I don't know this and I don't know this. With two unknowns, we cannot calculate the third one of it. So what I need two known so that I can figure out what's the third unknown. So if I can calculate eta, then I will manage to figure out what's the speed of light in glass. So I'm trying to figure out eta. For that, I have angle of incidence and angle of refraction. So I'm trying eta equals sine I, which is sine 55, divided by sine 33. Use calculator, and eta is 1.5040 dash dash dash, approximately 1.5. Okay, I will use 5 numbers because this is premature answer. Premature means it's not final answer. All right, so I'm using 1.5040. Whenever you have premature answer, you can use 5 numbers, 5 significant figures. Now I'm using this equation. So eta is 1.5040 because it's refractive index of glass. Speed of light in air, so it's given 3 times 10 to the power 8 equals speed of light in glass, which is medium, right? Here, speed of light in medium, and which is glass here. So speed of light in glass equals 3 times 10 to the power 8 divided by 1.5040 dash dash dash. So I can use 3 numbers, 3 significant figures. So answer is, you can use 5 numbers. It's 200,000. Better to use 5 numbers. Why did I take 3 times 10 to the power 8 over 1.50? Because if I take 1.5040, it is bit less than 200,000. But then you can cross check what options are closest to, which option is closest to that. So which is that. So my answer is that. 23. Which statement about the image of an object formed in a plane mirror is correct? Okay, plane mirror, it is always, remember, smaller than the object? No. It is the same size as the object? Yes. Larger than the object? No. It is inverted? No. Always remember that, always visualize that you are standing in front of mirror. So when you're standing in front of the mirror, do you look yourself, your image, as smaller? No. Same size? Yes. Larger than yourself? No. Is it inverted? Inverted means upside down? No. So answer is B. 24. An object is placed in front of a thin converging lens. The diagram shows the paths of 2 rays from the top of the object converging lens. An image of the object is formed on a screen to the right of the lens. How does this image compare with the object? So first of all, let's draw. Okay, one is parallel to principal axis, which is principal axis, then passing through the principal focus, the other one passing through the principal focus. Wherever these two meet, there is my image, sorry. All right, now that is larger than, yes, it's larger, and upside down. Upside down means inverted. We have done this, so we are not doing this. We have done this. It's the, I think by mistake it is photocopied again, or maybe it's the same answer questions in the, okay, this is same questions in 2 papers, I think. So that's done. Okay, question 6a. Figure 6.1 shows ray of green light passing through a prism. A ray of blue light is directed towards a prism on the same path as ray of green light. On figure 6.1, draw the path of blue light through and out of the prism. All right. If I know it's wave gear, the white light is diffracted in 7 colors. So violet the bottommost and topmost is the red one. After violet it's indigo, then blue, then green. So blue is just before green. So it goes like this, just next to that line, and I can say that. All right. The wavelength of the blue light in air is 4.8 times 10 to the power negative 7 meters. Calculate the frequency of the blue light. What I know is the speed equation. V equals F times lambda. V equals speed equals frequency times lambda. Speed of the light, I know 3 times 10 to the power 8. Frequency, that's what I'm calculating. And wavelength is given 4.8 times 10 to the power negative 7. Send it to the other side. So 3 times 10 to the power 8 divided by 4.8 times 10 to the power negative 7. And use calculator, you get 6.25 times 10 to the power 14. Make sure that you use brackets for the calculations. So it's open bracket 3 times 10 to the power 8 ABC, or divide by open bracket 4.8 times 10 to the power negative 7 close bracket again. And answer is 6.3 times 10 to the power 14 hertz. Let's try the next one. It's magnet. So we'll try in the electricity and magnetism. We are not doing it now. We'll remember to do this in electricity and magnetism. Question number 21 from IGCSE Physics 0625, paper 23, June 2021. It says, a water wave passes into region where the wave travels more slowly. As it passes into the slow region, what happens? We have done this question, right? So if you notice, the questions do repeat themselves because it's very limited. So your core knowledge should be very clear, your concepts should be clear, and core knowledge should be very good one, so that you can answer those few questions. There are not many questions. All right. So it passes to the slow region. What happens to the frequency? And what happens to the wavelength? The frequency we had discussed, it remains the same, and the wavelength decreases. Light traveling at a speed of 3 times 10 to the power, okay, we have done this also. Number 23, a beam of light is monochromatic. What does monochromatic light mean? Monochromatic light means a light with one frequency only. So let's read the options. All the waves in the beam must have the same frequency. Yes. All the waves in the beam must have the same amplitude. No. Amplitude can be large or more small. All the waves in the beam must have the same speed only. No. All the waves in the beam must have the same amplitude, frequency and speed. No. That's A. An object is placed in front of a converging lens, right? The diagram shows the path of 2 rays from the top of the object. An image of the object is formed on a screen to the right of the lens. How does the image compare with the object? So let's extend. And then, okay, that's larger and inverted. Larger and same way up, no. Smaller and inverted, no. It is smaller and the same way up, no. All right. Which row correctly describe what happens to the frequency and to the speed of electromagnetic waves, where as we move through its spectrum from gamma rays to radio waves. Gamma waves to radio waves, we have written the notes, right? The frequency decreases and speed remains the same. Speed is always the same for all the waves. All right. The diagram, electromagnetic waves we are talking about. All waves means from electromagnetic spectrum we are talking about. The diagram shows a model of a sound wave passing through an air in an open tube. What is the region Q? Okay, region Q, if you see, this is compression and this is rarefaction. Again, compression, rarefaction, compression, rarefaction, compression, rarefaction. All right. So Q looks like it's a rarefaction, right? So it's a compression, no. Compression, no. Region with high pressure. Okay, so now first two, since it's not compression, I have crossed out. I didn't read further. Now rarefaction, yes. Rarefaction, yes. A rarefaction which is region of high pressure, or rarefaction which is region of low pressure. If you see, more molecules, air molecules reach high pressure, and less molecules low pressure. So that's high pressure wrong, and low pressure yes. So the answer is D. Let's try the next one. It's the same question again. We know it's copper and aluminium, right? Let's try this. Figure shows wave on a sea approaching a harbor, right? On figure 5.1, draw 3 wave crests in the harbor. All right, so I draw 1, 2, 3. They all should be of the same wavelength, and the distance between them, like this should be equal, right? So 2 eyes. Okay, it can't be exactly the same. 2 eyes, to my eyes, when I see, I should see they are nearly the same. All right, another harbor has a much wider gap between its wall. Describe and explain how the pattern of waves crust in this harbor is different from pattern you have drawn in 1. Description: waves pass through gap, remaining, instead of bending, they are a bit straighter, remaining straight. Because if the gap is this much, for example, gap is this much, and the waves are passing, then they pass just like that. That's what we are saying. All right. Explanation. What is the explanation? Less or no diffraction occurs. They don't bend. A sound wave of frequency 850 Hz travels through the seawater. The speed of sound in seawater is 1500 meters per second. Calculate the wavelength of this sound wave in seawater. All right, let's try this. Now, speed equals frequency times wavelength. So V equals F lambda. Speed is 1500. F is 850, right? Sorry. Yes, 1500 is speed and 850 is the frequency times wavelength. So 1500 divided by 850 is lambda, which is 1.76470 using calculator. Therefore, lambda is about approximately 1.8 meters. Do not forget to write units. All right, let's try the next one. Figure 6.1 is a full-scale diagram of a lens and an object O. That's object O, that's the lens. All right. The focal length of the lens is 3.5 centimeters. So I take a ruler and I draw. I can't use ruler. Let me try to use ruler here. I will try my best, but it can't be the exact. It won't help much. but I can show you, I can send you the picture on PDF. All right, 3.5, I'm trying my best. So that's somewhere the, okay. Now I'm, without doing that, I'm just drawing roughly. Let's say 3.5 is here. I can show you at home, sorry, I'm so sorry, in school. So that's 3.5, that's focal length, and the distance is 3.5 centimeters. So the other side also is 3.5 centimeters. So let's say this is 3.5, so it's about the other side focal length. All right, it's not exact, forgive me, I can't use it, I'm finding it difficult to use on the screen ruler. So I draw that, then it passes through the principal focus on the other side, then the other one passes through the centroid. So that's centroid, and then I extend this where those two meet. All right, there you will get the image, but it's not exact as I have said. I will send you in PDF, so it will be easier for you to understand. All right, the next one, the third one should pass through the according to the lens, because the machine, photocopying machine, changes the enlargement scale ratio of enlargement, so it can't be exact. And mine, what happens is, sorry darling, even my focal length is not also exact. So let me draw and then adjust the focal length. So let's say this is focal length. They all meet at one point. All right, that should be the case. All right, on figure 6.1, draw 3 rays to locate the image. Done. Draw an arrow to represent the image. Done. And label the image I. So that's I. Say 3 properties of the image I. It's real, yes, because I can focus it on the screen. It's inverted upside down, and it is enlarged. Next one. A student incorrectly states that the lens is being used as magnifying glass. State how the image produced by magnifying glass is different from image I. Okay, image produced by magnifying glass is upright, because if we are using magnifying glass to read the letters, small letters from the book, then if the letters are upside down, then real image upside down. Real image is the other side of the lens, we can't read. If it is upside down, we can't read. So it is first of all, it is upright image. The student moves the object O to the position P so that the lens shown in figure 6.1 acts as a magnifying glass. On figure 6.1, mark a position for P. Always remember that whenever you are using any lens, right, as magnifying glass, then you have to hold it between the principal focus. You have to hold the object between principal focus, right, and focal length. So sorry, principal focus and centroid. So that's the one. It can be here, object can be here. So this is P. So let's not draw the arrow. They haven't asked you to draw arrow. They just asked you to mark the position anywhere between F and C. C is centroid here. All right. Number 3. The students move the object O to a position. That's done. Let's try the next one. 17. That's IGCSE Physics. This is IGCSE Physics. 0625, paper 23, November 2021. The diagram shows waves in a ripple tank containing water. The waves approach a barrier and pass through the gap in the barrier. The size of the gap is about the same size as the wavelength of the ripples. The gap is increased. What happens to the ripple pattern to the right of the barrier? The ripples are closer together or ripples are further apart? No, not closer, not further apart. Ripples are moved more curved? No, but they are less curved because this gap is more. They are less diffracted. Number 18. The diagram shows a wave. Which row correctly indicates the amplitude and wavelength of the wave? Okay, amplitude. So let's check what's amplitude. That's amplitude, right? All right, that's amplitude. And what's wavelength? Wavelength, okay, it can be from top to top or mid to mid or bottom to bottom. All right, let's see. Amplitude, the distance between 1 and 2. Yes, correct. The distance between 1 and 2. Yes, yes. Okay, let's try. Sorry, I'm so sorry. Then the distance between 1 and 3. No. 1 and 3. No. All right, 2 are correct. Let's try the wavelength. Wavelength is the distance between 4 and 5. No. The distance between 4 and 6. Yes. The distance between 4 and 5. Yes. And the distance between 4 and 6. 4 and 5. No. And yes. So let's try which one is correct for both. So that's B. All right, let's try the next one. Two beams of light. That's question number 19. Question C1. Complete the path of the ray of light to the left hand end of the fiber. So that's, you can try this. Then internal reflection again the internal reflection, and then again outside. You can show like that. Name the process taking place at X. That's total internal reflection. Let's try the next question. That's IGCSE Physics 0625, paper 23, November 2021. In the diagram, the mountaineer can hear the system, although he cannot see it. When he is closer to the gully, he can both hear and see the stream. When he is further from the gully, he can neither hear nor see the stream. Which statement is correct? As he is approaching the gully's edge, he hears first the short wavelength, higher frequencies, and then long wavelength, lower frequency. That is right. Second one. So he hears first the short wavelength and higher frequency, and then the long wavelength, lower frequency. Perfect. As the approaches the gully's edge, the sounds become louder. Amplitude, no. He hears the stream because some of the sound is diffracted. No. He hears the stream because some of the sound is reflected from the opposite wall of the gully. No. Because the question says the mountaineer can hear the stream although he cannot see it, right? When he is closer to the gully, he can both hear and see the stream. The question, it says, as he approaches the gully's edge, he hears first the short wavelength, higher frequencies, and then long wavelength, lower frequency. That's the perfect answer. Which row correctly defines the frequency and the speed of wave? All right. Number of frequency. Okay. Frequency and speed. Okay. Frequency is number of waves. Or no, not number of waves. Number of waves passing per unit time. Perfect. Frequency is number of waves passing in unit time. All right. What is speed now? Distance traveled per unit time. Yes. Not the time taken for one complete wave to pass a point. No. Distance traveled per unit time. Yes. Time taken for one complete wave to pass one point. No. So where are both correct? That's C. Let's try the next one. Number 19. A ray of light travels from air into glass block. Speed of ray in air is VA and glass VG. Wavelength of ray in air lambda A, in glass lambda G. Frequency of ray in air FA, in glass FG. 3 suggestions as to how refractive index in glass eta can be calculated are listed. So eta is VA over VG. In air or vacuum over medium. Perfect. Correct. Eta equals, that is, all right, lambda A over lambda G. Lambda is the wavelength. So wavelength is, what is wavelength? Wave equals speed equals frequency. Okay, fine. That's in measured in meters, right? So eta can be wave lambda A over lambda G. Yes, it is true. And eta is FA, frequency over frequency. No, that's not correct. It can be speed over speed, right? Then wavelength over wavelength, but not frequency over frequency. Correct. Which suggestions are correct? 1, 2, 3, no. 1 and 2 only, yes. 1 and 3, no. 2 and 3, no. Number 20. The diagram shows a ray of light in air incident on a glass block. The diagram shows a ray of light in air incident on a glass block. Some of the light is refracted and some of the light is reflected. 2 angles P and Q are marked in the diagram. I think we have done this, right? Yes, it was done. Which row gives the angle of incidence and states whether total internal reflection occurs? This total internal reflection doesn't occur because some of the ray is refracted and some is reflected. And angle of incidence is Q. So that's Q and no internal reflection. So that's C. A photographer sees his image as shown. Photographer and image. What could X be? Mirror, translucent glass block, transparent glass prism, or transparent semicircular glass block? See, his image is shown at the back of that glass block, right? It can be, no, it's not glass block, it can be mirror. The sun emits infrared radiation and light. Light from the sun reaches the earth in 8 minutes. Which row gives the correct information about the infrared radiation? All right. Wavelength of infrared radiation. It's longer than the light. Yes. Longer than the wavelength of light. Shorter? No. Then wavelength of light? No. It takes same speed? Yes. More than 8 minutes? No. So both correct is A. Which row gives the typical value of speed of sound at room temperature in the material stated? Speed of sound in air, it is 340. Perfect. Water 1500 and iron can be more. Looks correct because in air solid it will be more. We know air and water. All right. B 340. Perfect. 5100. That's wrong. So no point of this, we don't know. What iron, which is solid, has to be more than the water. Okay, air, that's wrong. It's 340, right? Water, 1500, correct. And iron has to be more than water. 3 times 8, 10 to the power 8. That's light, speed of light. Speed of light, speed of light. So which is correct? All are correct. That's sound waves that are so loud that they damage human ear. What is ultrasound? Sound waves that are so loud? No. Sound waves that are too high pitched for humans to hear? Yes. Sound waves that are too low pitched? No, for humans to hear. It's like human hearing is 20 to 20,000 hertz, and sound wave ultrasounds are after that. Sound waves that are too quiet for humans to hear? No. Question 6. IGCSE Physics 0625, paper 43, November 2021. Describe an experiment to describe the speed of sound in air. State the apparatus you need, details of how to take measurements, and how to calculate the speed of sound in air. You may use the space below to draw a label diagram as part of your answer. So you can try like this. You are standing by this wall. 2 people are standing by this wall. One person has 2 blocks which is hitting against each other to make sound. Other person has speed meter. And what else do we need? Okay, measure tape and everything, all other equipment that he has, right? So once this person claps, he sees the person, or maybe because let him stand there, because he shouldn't be close to the person. He stands there. If he stands there, all right, that can be done because he's listening to echo. All right, I'm trying about echo. First I was trying about the person standing far so that he hears here the sound when he hears here, but let's use echo. So the sound travels there, and as soon as this person, the person A, hits the blocks, wooden blocks, the person B switches on meter. Which meter it is? The timer, right? Timer, he is timing. So when the sound comes here back, he will hear the echo. So he measures the time for echo, right? Let's think about what things that he needs. All right, so 2 wooden blocks, right? 2 things he needs, equipment, right? Or apparatuses. 2 wooden blocks to produce sound by heating them together. Stopwatch. Okay. Long tape. All right. Then we need walls. We should be around the walls. Then meter tape. All right. Long tape, meter tape is the same thing. So it's okay. Next one, timer. Microphone, so that when this person is making sound, there is microphone there. All right. Or oscilloscope, but I'm done with I'm happy with microscope. Okay, how to do that? Start stopwatch. Stopwatch. The person B starts stopwatch. When you see the person heating the blocks, right? And stop it when you hear the sound of echo. And then use speed equals, because distance is, this is also d and this is also d, 2 times distance measured between the walls over time that we have calculated for echo. That's how we measure. Okay, that's fine. Let's try next. Sound waves from television and sound waves from a television are diffracted. Sorry, it's very little, very small words. Let me use, okay, fine. Sound waves are from television are diffracted through doorways. Light waves from a television are not diffracted through doorways. Suggest why light waves and sound waves behave differently in this situation. Because the wavelength of light is much smaller, so the width than the width of doorway, so they will travel without diffracting. But the wavelength of sound is larger, so they can diffract and pass. Okay, so wavelength of light is much smaller than width of doorway, or we can say, or wavelength of sound. So sound does not diffract, so sound does not diffract okay, it should be wavelength of light is much smaller than the width of doorway, so diffraction does not occur. Wavelength of sound is nearly equal to the doorway, gap of doorway, so it diffracts. For diffraction to occur, wavelength should be larger. Or equal to the gap. Okay, now let's try. Figure 7.1 shows ray of green light emerging from one face of glass prism. On figure 7.1, draw the path of green light entering and passing through the prism. The green light, okay, let's try that first. So that's the normal. Then the light bends a bit. Sorry. Then I draw normal there also. And then from there it goes away from the normal. As it enters, it is going towards normal, so this angle is small, and then as it goes away out from the glass to air, it goes away from the normal. All right, let's try the next one. The green light is monochromatic. State in terms of wave property what is meant by monochromatic light. Monochromatic light is light of single frequency. Light of single frequency. State the speed of light in air. 3 times 0 times 10 to the power 8 meters per second. The wavelength of green light in air is 5.2 times 10 to the power negative 7 meters. Calculate the frequency of green light. V equals F lambda. So 3 times 10 to the power 8 equals F times 5.2 times 10 to the power negative 7. I'm sending it to the other side. So 3 times 10 to the power 8. Don't forget to add brackets. 5.2 times 10 to the power negative 7 is F, which is 5.8 times 10 to the power 14. The refractive index of glass for green light is 1.52. Calculate the speed of green light in glass. Refractive index is speed of light in vacuum or air. Let's write vacuum, doesn't matter. Or over speed of light in medium. You don't write dot dots, please write the full thing. So eta, which is 1.52, is 3 times 10 to the power 8 over speed of light in medium. Medium is glass. So speed of light in glass equals 3 times 10 to the power 8 over 1.52, which is 197, 368, 421.1, approximately 200 million, which is 2 times 10 to the power 8 meters per second. All right. There was one question which was not done. It was from March 2021. March 2021, this was part of question 6. C was missing. This is C. We have done A and B. C was missing. Figure 6.2 shows 3 rays of green light passing through glass below. Rays of green light, glass blocks. These three rays of red light approach the glass blocks on the same path as the rays of green light. On figure 6.2, draw the path of these rays of light to the right of the glass blocks. All right, so rays of the light are passing, right, at the same, they approach the same path. So I'm using red color. They are taking the same path, right? So I'm using that. Then they reach the same, they and they, right? Now, once they enter, if you remember, Vibgyor, that's what I keep on saying. Violet diffracts the most, red diffracts the least. So it will diffract less. Sorry. It will refract less. So here also it will refract less. From there, again, when it comes out, since it has refracted less, it will just again refract less. This will pass straight through this. And this also will refract less. And we see the center where they three meet here, bit right of that. Okay, I'm done. Let's try the next chapter now. We are trying now radioactivity. Hope you understood everything. If you don't understand anything, please see me at